Okay, this is the chapter 6, chapter 6, chapter 6 physics. Okay, yeah, let's start. Which of the following facts support the idea that particles of a gas move more freely? Particles of a gas move more freely. Where is the pen? اشتغل. Move more freely than liquid. Okay, why do gases move more than the liquid? أول شيء because the diffusion rate of the gas is faster. And Brownian motion, remember what Brownian motion is? Remember if you had a container, خلينا نقول, okay, wait, let me make this a bit thinner. Okay, let's say you had this black container, okay, and you had smoke particles in it, okay? Smoke particles in it. These are big smoke particles. These smoke particles, if you, by the way, if you see, they will start moving. They have some random movement. Okay, this is what we call Brownian motion. Okay, so Brownian motion exists in all states, but you can only see the smoke particles moving. Do you look at water and do you say that the water molecules are moving? Can you see it? You can't, no? Okay, even though it does happen, but you can only see it in gases. So what does that show you? It shows that gases move more than a liquid. So that's why we pick this. Brownian motion in gas is actually readily observable because you can actually see the motion. So that means that they move more freely than the liquids. Okay, the speeds of different molecules in a gas are different. So let's say you have N2O, nitrogen NO2, sorry, nitrogen dioxide. Okay, this is the sample of nitrogen dioxide. They're all gas molecules. Okay, do they have different speeds than each other? Obviously not. They all have the same speed. Okay, all gases are hotter than liquids. Obviously, that's wrong. Boyle's law applies to gases but not to liquids. That's also wrong. I think Boyle's law was the pressure volume one, but that's not important. Okay, and well, these two are the important ones. Question 2. Which of the following describes matter in a solid state? Obviously, solids are closely packed. Do they move freely? Obviously not. Do they form ordered arrays? Yes, they do. When you have solids, they're all linked to each other in ordered arrays, like this. Let me, yeah, and then it goes down here, it goes here, continues here, here, here. So it's just a cube, it's all ordered. خلاص, it's like this. Okay, so they're all ordered, if you get what I mean. Okay, and one here. So that I'm just trying to draw it for you. Do they vibrate around fixed positions? Of course they do. You guys know solids all vibrate. Do they have the same speed? No, of course not. Question 3. Uh, what is true about the behavior of particles during vaporization? Okay, during vaporization, obviously matter absorbs heat. But for those who don't know, vaporization is going from a liquid to a gas. Okay, during vaporization, matter absorbs heat. Of course, right? You need to absorb heat to become a gas. Okay. During vaporization, the distance between the particles of a liquid increase. Of course, to become a gas, you need to split the bonds between these liquid particles. So they have to space out more. So the distance between the particles will increase. The distance increases. During vaporization, particles gain kinetic energy. No, okay, they don't gain kinetic energy. Vaporization, let's say you're boiling these water molecules, okay? When you're boiling it, the temperature of the liquid doesn't change, but these particles gain potential energy. Okay, why am I saying potential energy? Potential energy is important when you want to change states. Okay, to change states, you need potential energy. Potential, from the term potential, it means to change into something else. Okay, it has a potential to change into something else. So that's why when you want to change from a liquid to a gas, you're changing into something else. So the potential energy will increase. How about the kinetic energy? Okay, do they gain kinetic energy? No, only potential energy increases. But after they do vaporize and they evaporate, the kinetic energy of these after it evaporates, now it becomes, after it becomes a gas, the kinetic energy of the gas molecules are more than the liquid, okay? But it doesn't gain kinetic energy, it only gains potential energy during vaporization, okay? So the kinetic energy one is wrong, but the potential energy is correct. During vaporization, particles increase their speed? No. You're just changing from liquid to gas. After vaporization is when you can say they gain their speed. Question 4. Which statements correctly describe the advantages of the small steel balls in a vibrating chamber? Okay, this is an experiment in the book if you want to read. يعني, صراحة I found the book very useful. If you want, these 3 pages, they cover this topic really well. But this is the experiment. Okay, it's useful for 3 things, and it's bad for 3 things. It's useful because it allows you to see many particles continually bombard a flat surface to exert a pressure. What does that mean? يعني, they keep on shooting particles. So I think it's up here actually. Yeah, they keep on shooting these small steel balls at this surface, and they measure the pressure. Here, there's a barometer, I think, or a gauge. Okay, and that gauge measures the pressure coming whenever the 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 balls hit this surface. Yani basically what's happening. Let me change this to red. These are steel balls, okay, and this is a gauge, okay. What this gauge does is measure pressure. So they keep on hitting and blasting this gauge and this surface with metal balls, thus exerting a pressure. Okay, why is this useful? It allows us to see that it does exert a pressure similar to a gas. Again, for part B, when you increase the number of particles in the chamber, it increases the pressure. Why? Obviously, if there's more particles in the chamber, it's going to be more collisions with this surface. So if there's more collisions, obviously there's going to be more pressure. Okay, why is this useful? Because it allows you to compare it with the gas. The whole point of this experiment is to see how does a gas work. And no, it's called a gas model. See how does a gas work. So instead of the gas molecules, they put these steel balls, and instead of the container of the gas, they put this surface here. Increasing the vigor of vibration of the spheres increases the speed and in which they collide with the walls of the container, resulting in an increase of pressure. Blah 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 blah. Okay, just know if you increase the vibrations, then there's going to be more collisions, more pressure. Okay, whatever. Okay, then they say the model also has its limitations here. Okay, the model also has limitations. Molecules are not necessarily spherical. Okay, in this model, we're using spheres. You see, we're using spheres, but molecules are not spheres. So that's why this is one of the limitations. So molecules are not spheres, so not necessarily spheres. Some are spheres, some are not. So that's why you can't really rely on this experiment. Okay, uh, spheres exert a pressure only when they are continually agitated by an agitator. What does this mean? I'm going to summarize this. Okay, these spheres, they only start to move like if you guys know, we took Newton's law. If an object is at rest, it won't move until it's acted upon with an external force, right? So if you have these balls here, okay, they're not going to just suddenly start moving. They need an agitator. Agitator means yani, something to push it. Okay, if there's no agitator, then these spheres are going to end up to stop moving. Why is this bad? It's because if I have a gas container filled with gas molecules, okay, they will move without me doing anything. They have random movement, okay? They move without any agitator, without any external force. So that's why this is one of the limitations to the gas model with the spheres, because you're going to need an external force, you're going to need an agitator, as they say, okay, to push it, okay? Uh, see, if the agitator stops, the steel spheres will stop moving and they will not exert pressure anymore. Molecules exert pressure all the time without needing an agitator. But moving steel spheres while undergoing collisions, they quickly lose their kinetic energy and they have to be continually supplied with kinetic energy from the agitator. Same thing basically. So if let's say you got an agitator and you pushed it, right? It's gonna last for maximum maybe 3 seconds. Okay? So that's why another limitation is that you have to continuously agitate and push it. So this also is another one of the limitations. We're done here. Okay, so to answer this, what are the advantages? Okay, the advantages are that they will exert a pressure just like gases. Increasing the vigor of vibration increases the pressure. We said that. And increasing the number of particles will also increase the pressure. Did we say all molecules are spherical? No, we said all molecules are not necessarily spherical. Did we say steel balls collide with the walls without losing kinetic energy? No. We said the balls will quickly lose Ke. They will lose their kinetic energy fast. Question 5. Okay, how does increasing the absolute temperature of a gas affect its kinetic energy? Obviously, if you increase temperature, then the kinetic energy increases. Remember that uh, kinetic energy is proportional to temperature in Kelvin. Okay. Question 6. A fixed amount of gas kept at, okay, these calculation questions. Okay, V1 is 3, P1 is 120. If the volume increases to 4, so this is V2, what's going to be the pressure? So P2. So we have V1, P1, V2, P2. You can use directly uh, P1 V1 equals P2 V2. Okay, you can use this, or you can say P1 V1 equals nRT1, and then P2 V2 equals nRT2, and then cancel R with R, N with N, because no moles are mentioned. Then they set constant temperature for T with T. You'll be left with P1 V1 equals P2 V2. Okay, whatever you want, or you could just memorize the rules straight away. And I like using PV equals nRT because it helps me understand more. Whatever. Okay, so let's do it. P1 V1, you're going to be left with P1 V1 equals P2 V2. So 3 times 120 equals 4 times P2. Okay, you're going to get 360 equals 4 P2. P2 equals 90. Okay, question 6. A fixed amount of gas is kept in a rigid vessel. Initial temperature is 300, so T1 300. Okay, pressure is 280, so P1 is 280. Okay, pressure of the gas drops to 180, so high P2. Okay, the temperature becomes, they want T2. Okay, again, we can use P1 V1 equals nRT1. P2 V2 equals nRT2. R with R, N with N. Okay, a fixed amount of gas. Since we're saying fixed amount of gas, that means the volume is constant, right? Constant volume. So cancel V with V. So you're going to get P1 over P2 equals T1 over T2. P1 is 280. P2 is 180 equals T1, which is 300 over T2, which is 193. Okay, not 193, sorry. We don't know T2. The answer is 193, but we don't know it. Then cross multiply. Let me do it on my calculator. 180 times 300 divided by 280, and you get 192.8. Okay, and they're saying one decimal place. If you round it, you get 193. Okay, question 8. Okay, matter has no definite shape and volume. So the shape changes and the volume changes. Obviously, that's a gas, because the gas, no matter what container you put it in, the shape of it will change. And no matter what the size of the container is, the gas will always occupy the volume of its container. So the shape and volume are both indefinite. They're not definite. Interactions between molecules is the strongest. Obviously, solids. Okay. Solids have the tightest and strongest interaction. The molecules vibrate, of course. Again, that's a solid. Matter takes the shape of the container. If you match it only to gas, of course you'll get it wrong, because also liquids take the shape of the container. You could have a water bottle that's a square and you have water in it, and the water will take the shape of the square water bottle. And if you pour it into a star-shaped water bottle, uh, so whatever, okay, that's bad. That's too bad. Okay, let's say a moon-shaped water bottle. Okay, no, that looks weird. Okay, like this. Okay, if you put it into this, the water will also take the shape of the moon, right? So it takes the shape of the container. So both the gas and liquid, okay, take the shape. Question 9. Okay. Uh, the smoke particles undergo small random movements due to the collision with the fast moving air molecules. Okay, you remember, Anna, I spoke about the smoke particles and Brownian motion. I told you if you have a container, okay, and you looked at the smoke particles inside, okay, These are the smoke particles. Okay, they would have movements, right? Random movements, and we call this movement Brownian motion. Okay, but scientists needed a reason. They needed some proof. They asked themselves, okay, طب why does this happen? Why does Brownian motion occur? Why is it random? Okay, so they invented a new term called molecular motion. Okay, molecular motion basically is if you zoom in more. Okay, well, we're looking at this using a normal microscope. Okay, if you zoom in more, you can find tiny dots. Okay, and these are all the millions and billions and trillions of air molecules. Okay, these are the air molecules. So what happens is these air molecules, since it's a gas, right? It's a gas, and gases they move randomly. So what does this gas do? So it moves randomly. Okay, so once it moves in this direction, it's gonna bump into the smoke molecule. So what's gonna happen? This smoke molecule, as a result of the collision with the air molecule, is gonna move. So this Brownian motion isn't entirely random. It occurs due to the molecular motion of the air molecules. But scientists say this is a hypothetical theory. Okay, it's hypothetical because they haven't been able to prove it and zoom in and see the air molecules because the air molecules are too small. They just kept this hypothetical, and for now it's just a theory. Okay, in the molecular motion, it's in it's it's in the book. Uh, but so you have to know it since it's in the book. So Brownian motion occurs due to molecular motion, which is basically the collision with the air molecules. Just go smaller. What's smaller than smoke? Air. Okay. Question 10. Uh, okay, a gas is sprayed inside a sealed container. When the gas particles move, they hit the sides of the container. This creates pressure. Okay, what happens if you increase the temperature of the gas? What happens to the speed? Obviously, at a higher temperature, it will be faster, right? And when the temperature of the gas increases, what happens to the pressure? You guys know PV equals nRT. This is the way I do it. If you're on the other side, if you're on opposite sides, that means you're directly proportional. Okay, since we're speaking about pressure and temperature, right? Pressure is here, temperature is here. So that means they're directly proportional. So what does that mean? If two things are directly proportional, that means if this increases, what happens to this? It increases. So when the temperature increases, the pressure also increases. Question 11. The tiniest particle obviously is an atom. We can go next. Question 12. The random kinetic energy of a body's particles determines the amount of its heat energy. Always associate kinetic energy and velocity to heat because obviously the hotter an object gets, okay, the faster its kinetic energy will be. Okay, like think of temperature. Temperature and kinetic energy. The temperature and kinetic energy, they are always correlated. Okay. Question 13. Okay, 3 moles of a gas are stored in a 4-liter vessel at pressure 8.5 times 10 to the 5. Use R equals 8.31, the absolute temperature. Okay, obviously we have volume, we have pressure, we have R, we have moles, and they want temperature. So obviously we need to use PV equals nRT. Okay, pressure 8.5 times 10 to the 5. Okay, before continuing, actually, PV equals nRT in physics is different than the PV equals nRT of chemistry. And why? It's very small. It's a very small difference. The only difference is that in chemistry we used to use ATM for pressure, and for volume we used to use dm cube or liters, right? But in physics, oh, what happened? I don't know where that. Okay, PV equals nRT. It used to be for pressure we used to use ATM, and for volume we used to dm cube or liters, right? But in physics, we cross all of this out. For pressure, we use Pascal because the SI unit of pressure is Pascal. And for volume, we don't use dm cube, we use meter cube. Okay, I'm gonna write the conversions for all of these now. From Pascal, to sorry, ATM to Pascal. Was it ATM to Pascal? Wait. ATM to Pascal. Yeah, ATM to Pascal. You do times 10 to the power of 5. Okay, Pascal is bigger than ATM always. Okay, it's bigger. Pascal is always bigger. That's why you always see times 10 to the power 5 times sometimes you see times 10 to the 6. Pascal, if you want to go from ATM to Pascal, it's times 10 to the power 5. You rarely use this, okay, but just in case you need it. And then from dm cube to meter cube, you divide by 1,000, okay. Same thing for liter, because liters and dm cube are the same thing. So if you want to go from liter to meter cube, you divide by 1,000. If you want to go from centimeter cube to meter cube, you divide by a million. Okay, المهم, let's start. Here, let's do PV equals nRT. Okay, let's plug in the values. The pressure, it's in pascals, so we don't need to convert 8.5 times 10 to the power 5 times the volume. The volume is 4 liters, but we need it in meters cubed. So from liters to meter cube, we said we divide by 1,000. So 4 divided by 1,000 is 0.004. Okay, so times 0.004 equals N, 3. We said 3 moles, times R, 8.31. I said use R equals to, and times the temperature. We don't know it, right? We're trying to find absolute temperature. So put this in a calculator, and I think you get a decimal. You get a very long decimal. Let me try 8.5 times 10 to the 5 times 0.04 divided by 3 times 8.31. You get 136.381, whatever. Okay, and I just rounded it to 136. In the exam, they will mention 3 significant figures or 2 significant figures or 1 decimal place. They'll mention it in the exam. Okay, but 136 is what I took, and it should be correct. I want to see what the other answers are. Yeah, they rounded to 1 decimal place also. Whatever you want, but they will mention in the exam what to round. Okay, a fixed amount of gas is kept at a constant pressure. Okay, the initial temperature of the gas is 300 Kelvin, and its volume is 2 liters. If the volume decreases to 1.2 liters, its temperature becomes what? Okay, again, PV equals nRT, P1 V1 equals nRT1, P2 V2 equals nRT2. Cancel R with R and with N. Okay, constant pressure, so P with P, you'll get V1 over V2 equals T1 over T2. Okay, please don't mistake this V for velocity, please, because we're gonna have a question later where it talks about velocity. Okay, so please don't mistake it. It's volume, not velocity. Okay, V1 over V2 will be 2 over 1.2 equals T1, which is 300 over T2. Cross multiply 180. And you don't need to convert to meter cube since they're both in liters, huh? Okay, and I explained this in the term 3 week 1 physics CA. But no, in details I explained it in the other quiz. But I'm gonna just give a brief explanation. Between 0 minutes and 1 minute, okay, which is over here, from here to here, okay, the temperature is going down. Okay, in the heating curve and cooling curve, we have kinetic energy and potential energy, and there's one rule. Okay, you can't have both of them changing at the same time. Either the kinetic energy changes or the potential energy changes. How do I know which one's changing? If the temperature is changing, that means kinetic energy is changing. Okay, temperature and kinetic energy are always associated. So if the temperature is going down, that means kinetic energy is going down. And since we have the kinetic energy changing, that means the potential energy has to stay quiet and it doesn't change. Okay, so the potential energy doesn't change. So here it remains the same. How about in 10 minutes, 15 minutes? So 10 minutes, 15 minutes. It has a constant temperature. So let's see, KE and PE. Which one changes? If there's a constant temperature. If the temperature is not changing, what will happen to kinetic energy? It stays constant. It remains the same. However, since one of them has to change and it's not kinetic energy, that means the potential energy will change. Okay, will it decrease or will it increase? That depends on the type of curve you're working with. Since we're going down, it's a cooling curve, so obviously potential energy will decrease. How about the kinetic energy between 20 and 22 minutes? So from here to here. Okay, since temperature is going down, what does that mean? Kinetic energy will go down. And since kinetic energy is changing, that means potential energy will stay constant. Okay, so kinetic energy will decrease. Question 16. When the body of a liquid evaporates, when it evaporates, huh? We're not saying during vaporization, no. We're saying after it evaporates, okay? Only its fastest molecules have enough kinetic energy to overcome the attraction from the other molecules. The molecules that remain in the liquid have less kinetic energy and the body has lower temperature. I think it's pretty self-explanatory, but I'll explain it, okay? You have water. At the surface of the, this is one boiling, okay? Imagine there's heat here, okay? There's a gauge over here. It's a Bunsen burner, okay? Uh, and you're boiling these water molecules, okay? There's water molecules here, here, everywhere, right? In the sample. Only the ones at the surface will actually evaporate first, okay? When it evaporates, these ones have higher kinetic energy because now they evaporated, they're out in the air, they got out, they escaped the forces of attraction, okay? Because in the liquid there's forces of attraction between every single molecule. So to change into a gas, it needs enough kinetic energy and enough potential energy to overcome this force of attraction. So the ones that get out, they have enough kinetic energy to overcome the attraction from the other molecules. However, the ones that are down here at the bottom of the liquid that still didn't evaporate, they have less kinetic energy. Okay, they're still not moving, they're still part of the liquid. Okay, and since obviously less kinetic energy, so lower temperature. Question 17. Okay, what phenomenon is this? Obviously, when the molecules spread out, then it's called diffusion. Underline the state of matter in which the rate of this phenomenon occurs the fastest. Obviously, diffusion occurs fastest in a gas. I don't think I have to explain this. The kinetic energy of the random molecular motion is called heat energy. Again, always associate the energy of the kinetic energy into heat energy. Well, think about it like this, okay? Kinetic energy and temperature, they're related, okay? Temperature in Kelvin, again. But can you say temperature energy? No. Which energy is related to temperature? You guys know it's thermal energy, right? Which is the same as heat energy. Okay, just call it heat energy. Question 19. Okay, underline all states of matter in which diffusion can occur. Okay, in my opinion, solid is correct. But I think in this question, uh, they xed out solid because it occurs so slowly in a solid that it's pretty much negligible. Okay, it's negligible in a solid because it's too slow, okay, in a solid. But in a liquid and gas, it occurs almost instantly. And when you put sugar, you dissolve it in a liquid, you see the sugar molecules, they spread out evenly into the liquid. So in يعني, a matter of at least 30-40 seconds. And in a gas, it's almost instant. That's why in a solid, it's too slow to be counted as diffusion. I think that's why. No, it's negligible. Okay, this one we're gonna use a new formula. Formula we really haven't seen before. Okay, I'm gonna explain why, and then you'll see. Okay, the temperature of a gas is 1000, so T1 is 1000. The average speed, the speed, let's call it S1, is 600. The temperature of the gas decreased to 250, so T2 is 250. What's gonna be the speed, the new speed, S2? Look, speed 1 over speed 2 equals radical T1 over T2. Uh, in the formula, they say V. Okay, in the formula, they say V1 over V2, and they refer to this as velocity. But I don't want to confuse you because we're working with both. We're working with both volume and velocity, which are both two V's. So keep it as S. Okay, I don't want to confuse any of you to think it's volume. So just keep it as speed 1 over speed 2 equals radical T1 over T2. Okay, but to prove this formula, just so you can understand, okay, I'm gonna have to use V. Okay, so I'm gonna use V just for you. If you want to write it as S, you should get the mark easy. It's fine. Kinetic energy, okay, is related to the temperature, right? We said kinetic energy is related to the temperature in Kelvin. So we know kinetic energy is equal to half mv squared. Some of you might not know this, it's fine. It's an old formula from grade 8 and 9. Okay, kinetic energy is half mv squared. Okay, so kinetic energy 1, okay, kinetic energy we said, sorry, it's the temperature in Kelvin. So instead of saying kinetic energy, I can just say temperature. Okay, temperature in Kelvin equals half mv squared. So T1 equals half mv squared, okay, and T2 also equals half mv squared. And let's call this V1 and V2, right? So obviously it's the same mass, right? It's a mass m is the mass. So we can just cancel this half m and half m, and you get T1 over T2 equals V1 squared over V2 squared. And to get rid of the square, they decided to put a radical on both sides, and you get V1 over V2 equals radical T1 over T2. This is how you derive the formula for those interested يعني just to help you better understand it. فكل هالحكي على الفاضي. Let's actually solve now. Okay, just some space to solve. So let's use this formula. V1 is 600, right? 600 over V2, we don't know it, right? The second velocity, we don't know it. We're trying to find it. Okay. Uh, T1 is 1000 and T2 is 250. We said radical T1 over T2, so radical. So you get 600 over V2 equals 2, because radical 1000 over 250 is 2. Okay, then you divide 600 by 2 and you get V2 equals 600 over 2, and you get V2 equals 300. Okay, over here 300. Question 21. Okay, what statement best supports the view that the distance between gas particles is large? Gases are compressible. Okay, if you're okay, you have this gas. Okay, again, let's call it NO2. Okay, and I get a piston, or I get a piston. Okay, I get a press, and I press it down. I can keep on going with the press and compress this gas all the way until it looks like this. Like this. I can compress it until it looks like this. Since I'm being able to compress it, that means there were spaces in between these gas molecules. If you're able to compress anything, that means there is space for you to compress. So how do we know that the space or the distance between the gas particles is large? Is that because we can compress it? Anything in general, if you want to see if it has a space between it, you see, can you compress it? Can you squeeze it in your hand? Does it compress? And in this case with gas molecules, it does. So that's why it has a large space since it compresses. Question 22. Okay, this one I don't like it. Okay, a diver produces a bubble of air which has volume of 2, and it's 5 meters below the surface of the river. Assume the temperature is the same. Okay, take G equals 10, atmospheric pressure is 100 kPa, and the density of water is 1000. Okay, what is the pressure on the walls of the bubble just after it was released? Okay, so the diver, okay, let's draw it in blue. Maybe that will help. Okay, you have this is the ocean over here. Okay, and the diver is, I'm not going to draw the diver, but he's 5 meters below and he blows a bubble. Okay, the volume of the bubble is 2 milliliters. Okay, so they're asking the pressure on the walls of the bubble. Okay, remember this is from chapter 5. What's the pressure when you're underwater? The pressure when you're underwater, especially when you're in the ocean, okay, there's pressure coming in from the liquid. Okay, so the total pressure equals the liquid pressure plus the atmospheric pressure coming from the outside. Okay, so plus atmospheric pressure. So let's find this. Pressure total equals the liquid pressure. If you remember from chapter 5, well, you should remember it, you have it in this exam, rho gh plus atmospheric pressure, which is 100 kPa. Okay, and rho gh in this case will be pressure total equals rho gh, so the density of the water 1000 times 10 times the height 5 plus 100 kPa. I'm going to continue over here. You're going to get the total pressure. Whoa, you're going to get the total pressure is 1 2 3 4 4 zeros 5 50,000 Pascal plus 100 kPa. You can't add these because this is in Pascal and this is in kilopascal. So you have to convert this to kilopascal. How do you convert anything to kilo? You divide by 1000. So it becomes 50 kPa plus 100 kPa, and you get 150 kPa. Okay, most of these steps, if not all of them, you can do on the calculator, so it's fine. Okay, you get 150 kPa. Part B, okay, I'm gonna draw it again. the volume of the bubble as it's about to surface to the river. Okay, since you have pressure, okay, since you have the pressure, uh, you have the volume, you have that you have that the temperature is constant, and N and R are both constant. Okay, when you're changing pressure and volume, you have to use the rule PV P1V1 equals nRT1 and P2V2 equals nRT2 because we're changing pressure and we're changing volume. So they said temperature is the same, T with T. R always gets cancelled with R and is cancelled with N since N is not mentioned. So you're gonna get P1V1 equals P2V2. The first pressure, the pressure of the bubble when it was underwater. What's our first pressure? 150 kPa, right? So let's put 150. Just keep it 150 times volume 1. What's our first volume? 2. Don't need to change it because they're asking for the answer in milliliters, so no need to convert. Pressure 2. Okay, they're saying as it's about to surface to the river. Okay, so this bubble now, it's at the top. It's over here. Okay, what's the pressure of the bubble if it's right here? Is there any more? What's the pressure total? Is it liquid pressure plus atmospheric pressure? Is there any liquid pressure acting on the bubble now if it's at the surface? Of course not. It's not underwater anymore. It's at the surface. So only thing left now is the atmospheric pressure coming from the atmosphere and acting on the bubble. And that atmospheric pressure is 100 kPa. So P2, the pressure now acting on the bubble is 100 times volume 2 that we're trying to find. We don't know. You're going to get volume 2 equals 3 milliliters. Okay, so put your answer as 3. Question 23. A whipped cream charge is filled with N2O gas. Okay, the interior volume is 10 centimeter cube. It contains 0.18 moles. Use R equals 8.3. The pressure at 300. They want you to find the pressure at 300 Kelvin. Okay, so obviously we need pressure. We have volume. We have the moles. We have the R. We have the T. Okay, obviously we have to use P1V. Sorry, show P1V. Just PV equals nRT, right? PV equals nRT. And when you're only using PV equals nRT, what did we say? We have to have pressure in Pascal, volume in meter cube, and then moles, whatever. Obviously, temperature in Kelvin is already given in Kelvin. Okay, so let's solve this. Pressure, we're trying to find it. Okay, so just keep it as P times V volume. The volume they gave us is 10 centimeter cube. I need it in meter cube, and to go from we said centimeter cube to meter cube, you divide by 1 million. Okay, so if you divide by 1 million, you're gonna get 10 to the power of negative 5. Okay, I'm not gonna write 0.00001. Okay, I'm just gonna write 10 to the power of negative 5 equals the moles. Moles, they said 0.18 mole, so 0.18 times R, which is 8.3, times the temperature, which is 300. Okay, you're gonna get P equals 44 times 6, 44, I think 4 million, 44 million 800,000 or something like this. You're gonna get like a big number like this. Okay, but they're asking for MPa, megapascals. Megapascals means you divide by a million. So mega means you divide by a million. So if you divide this answer by a million, you get 44.8. Let me actually put it in my calculator. 0.18 times 8.3 times 300 divided by, yeah, you get 44,820,000. And after you divide by a million, you get 44.82, but they're saying one decimal place for 44.8. Okay. Question 24. The modern soda can hold beverages up to 600 kPa. So its maximum pressure, the pressure maximum is 600 kPa. Okay, assume the pressure of the gas when it's in the 20 degrees Celsius can is 300 kPa. So when it's 20 degrees Celsius, okay, when it's 20 degrees Celsius, the pressure is 300 kPa, and that the amount of the gas in the can is constant. So they're saying volume of the gas is constant. The temperature at which the can will burst. The burst means yani maximum pressure. So they want the temperature at the maximum pressure. When they say burst, يعني خلاص it's the maximum pressure. Okay, so they want the temperature at the maximum pressure. How would you find it? Okay, let's do P1 V1 equals nRT1, P2 V2 equals nRT2. Cancel R with R, N with N. They said amount of gas in the can is constant, so the volume is constant. So P1 over P2 equals T1 over T2. Pressure 1, we're saying 320 degrees Celsius, right? So 300 over 600 is P2, right? 300 is the first pressure, 600 is the second pressure. Equals T1. Okay, please don't put 20. You guys know temperature always has to be in Kelvin. So plus 273, and you get T1 is 293. Okay, so 293 over T2. Cross multiply, you get T2 equals, if I'm not wrong, it should be 586 Kelvin, right? But they want it in degrees Celsius, so you subtract by 273, you get 313. Okay, question 25. A fixed amount of gas at a pressure P, volume V, and temperature T. If due to a certain process the pressure of the gas has doubled, okay, and the volume has tripled, what will the temperature of the gas be? Okay, remember PV equals nRT. So, oh, where'd that go? Yo, what did I do? Hold up. Yeah. Okay, so we have PV equals nRT. Pressure of the gas has doubled. So that means I'm multiplying by 2 over here, right? And then the volume has tripled. So I'm multiplying by 3 over here. So in total, I'm multiplying by 6, right? So 6 times PV equals T, right? So basically, what happened to this temperature now? It got multiplied. It got multiplied by 6. Because what happens on this side also happens on this side. Okay, they're equal. So if you multiply by 6, you multiply by 6 here. That's it for chapter 6. Thank you so much for watching. Good luck in your exam.